Thanks everyone for joining. Hopefully, I will not disappoint you. So let's dive right into it. Um, Repurposing Scala's pattern matching for deeply embedded DSLs. What does that even mean? Um, so what I mean by that is I want to be able to write my DSL programs as if I'm writing Scala, including pattern matching. There's some pattern matching in this example. You might notice a different word than match that we use in Scala. We'll get to that. And when I write code like this is executable Scala code. Um, when this runs, it's going to produce my AST, my reified representation of my DSL program. And emphasis on my representation, on custom representation. I don't mean getting the Scala AST of this expression. I mean, you design your AST, you stay in control, and running Scala code produces your AST. Um, that means no macros, no macros manipulating the Scala AST. This is something, by the way, that Scala-Virtualized allow. Like virtualized pattern matching was one of its features, where you could override how pattern matching behaves. But yeah, Scala-Virtualized was a branch of a compiler and never made it to the mainline. So we will here do it by our own means without needing changes to the compiler. Okay, and a little bit of motivation of why, if you want to design a DSL, would you want to do something like this? Maybe you are asking, why do I need any intermediate representation? The answer is simple. That gives me freedom to interpret it in different ways than just running it. I could maybe draw a graphical visualization of my program and so on. Maybe why even embedding my DSL into Scala? And the answer is again simple, because I want to piggyback on Scala tooling, on the parser type checker development environment, and so on. Then you may ask, why why do I want to write my DSL as if writing, or very similar to writing Scala, but not quite? You saw the pattern match was not quite like Scala. Um, uh, like shouldn't DSLs read like English, like natural language? But my answer is, if you want some level of sophistication that uh, like ADTs and pattern matching, I would still like to piggyback on Scala for variable bindings and such stuff. So feel free to propose different syntaxes, different representations, but um, but yeah, that's not going to be easy if you want to retain piggybacking on Scala tooling. And then you might be curious, what kind of DSL would would require, or in what kind of DSL would I want pattern matching inside the language? And I'll give you an example soon, which will be our working example. So with that out of the way, um, some aspects of a DSL, domain specific language, is a domain, of course, and then, like with any language, there's syntax, there's internal representation of programs, and then there's interpretation, which usually is running the program, but there could be multiple, like also visualizing or serializing it and storing it in a database, or compiling or transpiling it to a different language, or simulate, and so on. And so this part will be our segments of this presentation, um, which we will go through, although I will not talk much about interpretation, I'll just provide a few notes about that. We'll mostly focus on the representation and the translation from syntax to representation. Now I'm going to introduce the uh, domain of our domain-specific language, and I chose workflows. So maybe what's a workflow? Here's definition from Cadence. A fault oblivious stateful function that orchestrates activities. Now, what is an activity? That is to be understood as some business level operation, typically a call to a REST service or something like that. It can be effectful and non-deterministic. It could potentially fail. And then on top of these business level operations, the workflow is the glue that that builds business logic on top of those operations. Um, uh, Workflow could be potentially long running, think like days or weeks. Could be like waiting for someone clicking a link in an email and filling some form. So it's not long running because it's so compute intensive, but it's just waiting for some service or human input. Uh, and crucially, it should be resilient uh, towards infrastructure failure uh, of the machine, of the hardware where it's running, and resilient with respect to activities failing intermittently, like the service being intermittently unavailable. Uh, and uh, why what's the added value of the workflows is that the resilience should be uh, out of the box without you persisting your state um, in a uh, in a database or somewhere. Okay, so that's workflows. I assume at least some of you have come across them. I'm going to give a quick example of a workflow, which would be in a company, employees can request equipment for work. Um, they can request a monitor or a chair, and they can request it for the office or for home. So here's a visualization of such workflow. First, the employee would ask for approval of this request, which could be declined or uh, declined or approved. And whenever we see there's a bit of color coding, whenever there's two parallel colors, that means only one of them will execute depending on yeah which branch is chosen. If it's approved, we branch again based on whether it's for office or for home. Uh, if it's for home, let's assume it's a single activity to order it from supplier, and if it's from the office, um, we then branch or pattern match whether it's the monitor or the chair. uh, but in either case, we also have the location uh, the, of the desk, so we will need that information, so we distribute that to each branch. Hopefully you can follow the diagram. And then if it was a monitor, we request it from the IT department. If it was a chair, we request it from office management. And the result could be successful, but also a failure of various reasons, or the request could be declined. Now this diagram uh, that that I draw here, I actually didn't draw it by hand, but generated from code, maybe with some minor retouches. So that's when I was talking about alternative interpretation. This is actually an alternative interpretation of the DSL. All right. So what would we need from such a DSL? Um, we need to express control flow. We saw a lot of branching there. Um we didn't see loops or concurrency in this example, but that's also something we would like to have. We would like to be able to define uh, our own functions. In fact, this whole workflow was kind of a function. It had an input, the request, it had some output, the result, and there were some subcomponents which also had this shape like functions. And we want user-defined data types. So for example, this equipment request or this item, whether it's chair or monitor, that's not something that can be built into the workflow DSL, but something the user of this DSL should be able to define themselves. And then, of course, we want to be able to execute such workflows durably, for which we will need to be able to serialize the current state and persist it somewhere. And as I said, we will want to be able to have alternative interpretations, um, and possibly uh, if we want, so we have this embedded in DSL in Scala for now, and then let's say we want to make it a full-fledged language, like an external DSL, build our own tooling. We would still like to be able to migrate our programs, to load up our programs written in Scala into this new tooling for external DSL without having to rewrite them. As I said, workflows are not a new idea. There's a bunch of solutions, um, for example, from temporal or cadence or restate golem, new one uh, for Scala workflows for us. So how do they address these requirements? Um, so for control flow functions data type, they say let's just use whatever the host language offers. So just use Scala functions, Scala types. Um, and then for durable execution, they make a realization. They don't need to be able to serialize the state of the workflow. They just need to recover it. So they can serialize some snapshot and then based on event sourcing, uh, whenever there's an activity, we would record an event that an activity started and how it ended. And when we need to recover the state, we would replay the log of these events, um, assuming the glue, the workflow glue is deterministic. It's only the events that could be non-deterministic. We reach the same state as when we crashed, let's say. So that's a nice realization, a nice trick. What about the rest? Um, well, alternative interpretations or migration path to external DSL without rewrite is simply not possible with this solution because exactly this, they don't have control over the representation of the program. Um, like visualization, for example, for them would mean visualizing the Scala program or the Java program, uh, which is a much bigger task than visualizing a limited DSL. So that's off limits for these solutions based on event sourcing. All right, um, we have covered the domain. And now a bit of a, before we proceed, a bit of a legend, because there are like multiple roles involved in working with workflows. The central one being the developer of the DSL, the person who's designing the DSL, and that's going to be you. That's who this presentation is targeted at. And there will be a bit of color coding of code snippets. So whenever there's a bit of code that's expected, you are expected to write, that's going to be in this yellow box. Then there's the user of workflows who uses the DSL to develop workflows, and their code snippets um, are going to be in blue. Then there's some business user that's running the workflow. That's in our example, like the person requesting uh, the equipment, and they are not expected to write any code. And finally, there will be some library code shown from a library Libretto Lambda, and that code will be shown in green. Okay, and so now let's move on to representing DSLs, uh, internal representation of our programs, something like an abstract syntax tree. So you've probably seen seen something like expression trees before, where we would represent constant values and then some operations like plus, and it seems all straightforward. Um, uh, what's the big deal? But things get more complex when you need to represent functions. Um, so then you need to make a decision uh, whether so you could say let's just use Scala functions in my AST, and whenever, so for example with the IO monad from CATS or from ZEO, there's usually a flat map operation which stores a Scala function in the AST. um, but there is a problem with this, that this Scala function is opaque and we cannot, for example, visualize what's inside. Um, so for this reason, for us, this is a dead end. We cannot look into Scala functions. So we will need to roll roll up our sleeves and represent functions as data, which uh, which is what deep embedding means. Um, so our AST will have no Scala functions inside, um, and we therefore will be able to introspect it and be in control of the representation. Okay, so how do we represent functions? Um, there are at least two common approaches. One is to just extend the data type that the expression tree that I showed you before with primitives to represent variables, which is just the name of the variable, and then lambda abstraction to define function where it's like the variable name that's the input of the function, and then the body of the function which could reference the variable, and then function application, applying a function to an argument. So for an example, what the DSL user would write is when they write this lambda expression represented in this representation would look like this. It quite mimics the structure uh, of the code. We introduce a new variable x, which is then used inside the body, and it's all an expression tree. On the other hand, we could go a different route, and spoiler, I will be I will be preferring the second one, even though that's less familiar. Um, where our AST, so our AST will be, we will call it the flow, already has two parameters standing for input and output, like a function. And that's why I call it function centric as opposed to expression centric. And there will be no variables inside. Uh, so the plus operation, notice how on the left the plus operation already contained the operands, whereas here it just captures the state that it has two integers as input and one integer as output, and we will also be drawing these graphically. Um, Another operation would be just to copy the input to two outputs. Um, Another operation would be sequential composition of two functions, parallel composition of two functions, and many more. Now, to represent the same user function in this representation, um, it's best to look at it graphically. We compose the operations, and there's a parallel composition in the middle, then sequential with plus, then another sequential composition with copying. All right, so these are two different approaches to representing functions. So let's compare them quickly. Um, the one with lambda abstraction and variables matches the syntax closer, uh, whereas the point-free function-centric needs a bit of translation from the syntax to the representation. Um, the uh, the one on the left is quite expressive with few primitives already, whereas uh, the point-free one needs more primitives. Um, we already saw these four ones, but there we will need many more. Already a trivial thing like identity will need to be represented, or just swapping the order of inputs, or um, regrouping, reparenthesizing inputs is also an explicit operation. Ignoring values is an explicit operation, or introducing constants is an explicit operation. Um, Building up higher order functions will need to be done with explicit carrying and applying it with explicit eval, uh, and more. So there are many primitives. Also, the one on the left is quite concise, even though we don't see it here. They seem somewhat equal size, but in general, the one on the right without variables can get more verbose. Uh, and as you probably noticed, the one on the left corresponds to lambda calculus, whereas the one on the right is inspired by categories. Uh, on the left, everything is a value, even functions are values. On the right, everything is a function, even values are functions. Constant value would be a function from unit to that value. Yeah, you could challenge the claim that that functions are values if it's closing over something from the context, from the outer context, like capturing arbitrary resources. But let's leave that aside. Um, and this like positive things that I listed have flip side. So uh, in this representation using variables, it's concise thanks to because I can reference a variable at arbitrary distance from where it was defined. Like it could have been I can reference variable that was defined somewhere in some outer lambda, uh, but that's a sort of non-locality which we do not have on the other side, where we can reach everything by locally following the wires as in the graphical representation. And then uh, this one has few primitives, but you cannot reasonably take anything away and still get something useful. Whereas in the other one, if I don't want higher order functions, I can just not include carrying and eval, and I'll be fine, and my language can still be useful. Or if I want linearity, I'll just not introduce primitives to copy values and ignore values. So I get more graded expressive power. Um, but the main reason I'm going to like the second one is that in the representation with variables, there's a lot of illegal state. You could mention a variable that was not defined. You have shadowing of variables, so you need to implement capture avoiding substitution. And it just is so scary to me that even if you check well-formedness, now you're going to manipulate your program. You break it apart into fragments, recombine it in another way, and hoping that you did it, that you did it right. That you haven't created, that the result is what you wanted. Whereas in the point-free representation, there are no illegal fragments and no troubles with variable shadowing or undefined variables, because there are simply no variables. And another reason I like the point-free function-centric representation is because it does have this natural graphical notation that I was showing. Okay, so we will be continuing with this sort of function-centric representation. Just a quick note to include values in our AST. So I already mentioned it will be a function from unit to a certain type and holding the value, but this can cause trouble, because this means I'm able to embed arbitrary Scala values in my AST, like a running thread, which is obviously nonsense. So we will need to be more defensive about what values we can represent in the AST. So we'll need to introduce some GADT uh, uh, that limits what's a legal value. Let's say constants and then pairs of values and so on, and then it becomes like holding a running thread in my AST would just not compile. All right, another bit of best practice, just to get more clarity about what lives at the Scala level and what lives at the domain level. Um, even even for common things like pairs or either or unit, introduce a new type at the domain level, just for clarity. uh, they can be, and I prefer when they are uninhabited at Scala level, which means they really cannot live at Scala level. So let's say they could just be defined as a sealed trait with no subclasses, so there will be no instances of those. And they will be used only in phantom positions in our AST. Um, so yeah, so since it's uninhabited, don't ask what it is, but ask what you can do with it. So we have, for this pair type, we have already seen it several times. For example, it's created by duplicating a value, or it's used for parallel composition, or the unit type is used for introducing constants, for example. Inside values, we have when we want the pair of values, that's also where the pair type shows up, and so on. Okay, that was a quick side note. And now I promised you we're going to see pattern matching and have a representation of pattern matching that's that does not allow non-exhaustivity. So what are we going to pattern match on? The answer is ADTs, um, in Scala 3 called enums, or family of a sealed family of case classes in Scala 2. So we'll, on our domain level, we will need to be able to represent user-defined enums. So where in Scala 3, we would represent the request, going back to our example, requesting equipment, as this ADT with two cases, each of them holding some data. Um, we'll need something domain level, but why? So why? Let's remind us why not just use Scala enum? Uh, well, first, I don't want arbitrary Scala values in the AST, the contamination problem. But also, in order to work with the Scala enum, we would need Scala functions, and that's a no-go for us. So we need a different way to express them. And so here's a snippet of what we will be going for. And it includes a bunch of types which we haven't seen before, but for now let's just notice that this type alias captures all the information of this that's in this Scala enum, except for the field names, but that's a minor detail. um, so what are these types? And notice the color coding. This is something your user would write. So, and you as the language author need to define these. So how do you define them? Um, Easy, as I just said. Let's just make them uninhabited. Um, just declare them as seal traits with no subclasses. Uh, but then ask what can we do with it? Well, it's now up to you to design. But what do we need to do with such ADTs? We need to be able to produce them, and we need to be able to consume them. Um, so to produce, um, we want to be able to produce each case, and by providing the necessary data. So we want functions from the data to request to the ADT, our enum, for both cases. And how do we consume? So in Scala, you pattern match and then handle each case. So we will need to handle each case. So we want some uh, we uh, we want if we have a handler of each case, we want a way to combine it into an AST that handles the whole ADT, all the cases. So well, that's what we want, and now we need primitives in our AST to support this. Um, the idea here is don't do anything, don't do much, just capture what you are trying to do. This is the same idea as with any free structure, like free monoid is um, you want to combine values, but you just record them both and know that that it's an operation on these two values. So similar idea. Uh, so you would design primitives in your AST like inject, which is injecting the data into a specific case, and like handle, which is handling all cases. Let's dig into just a little bit into them. So here's the definition of request, but let's rewrite it so that we get the cases separately. And now to create a request, we could use this inject primitive for the respective cases and providing the respective data. Uh, and here I'm omitting this member, which is uh, a type-safe evidence that for office is actually a valid case of cases, and the type there is equipment and desk location. And these result types are what we wanted, because enum of cases is exactly the definition of request. So this is how we capture functions creating our ADT. I'm not talking here about how we're going to interpret it, but this is how we capture the intent. And now this member uh, is from the library, actually. I'm not going to go into detail, but it uses like similar type level tricks like you use with things like age lists and such. Um, uh, and it makes like invalid cases unrepresentable. So for example, if there's no instance where the case name would be foo, because there's no such case, or the case name is okay for office, but the type should be desk location here, so that's also unrepresentable. Um, Now for handlers, again, just capture the intent. Uh, and so there's also a data type for that provided by the library, but just to give you an idea, handlers of cases like X and Y of specific types, the data structure for it would just hold the handler for each case. Um, and this is the key. This will be the key to making non-exhaustivity unrepresentable, because you cannot create handlers of cases such that any of the cases is missing. We don't yet know how we will translate the pattern match into this. We will get to that later. But yeah, this is key to that exhaustivity. One more thing about um, handling enums. So what if we have? We can only consume tuna with rice or cod with rice, but the handle primitive is only able to handle enum, not enum and something on the side. So in order to work around this seeming limitation, um, right, so we don't have anything to just handle tuna itself here. To work around it, we introduce another AST primitive that distributes the side dish to each case of the enum. We get a new enum here. Um, and then we can handle that because we have handlers for that. So we'll need to give this new primitive a name. Distribute RL as in from right to left. Um, and yeah, that's what you need to have as a primitive of your AST as well. And again, in a using some type level techniques, you can make this completely type safe, making illegal things unrepresentable, and there's also in the library there's a data type for that. Okay, so those were the basics of the representation that will enable making non-exhaustivity unrepresentable. Now, now we are finally getting to when I see that Scala code, how do I get the representation? But maybe, so why do we need any other syntax than just constructing the AST directly? And here's why. In the point free notation is good for the machine, is has a nice visual representation, but in code it looks terrible. And I mentioned it has this locality where you can chase the wires, but you don't see any wires in this textual form. And I find it much worse than the pointful expression oriented representation. So that's why we want some nicer syntax. Um, and this is the kind of syntax that I showed you before that we will want to achieve. Notice that we are using familiar Scala constructs like lambdas, uh, introducing variables, pattern matching, and forming expressions. So this is what we want. Uh, and how do we go from the left to the point-free representation that makes illegal states unrepresentable? So let's break down what we the constructs that we see on the left. What does this? How to implement this flow? Uh, what's this switch? What does that do? And how to define these extractors and what do they do? Flow. Uh, flow is uh, is a construct that compiles this Scala function into our AST. So it takes a regular Scala function and returns a flow that does not contain any Scala functions inside. And if you haven't seen this trick before, that might seem like magic, how to get rid of this Scala function. But if you have seen it, the trick is uh, it's working on auxiliary expressions. We'll get to it what this expert is. So your job as the language designer is to implement this flow function, which takes a Scala function and returns flow. Uh, you can use some handy tools from the library where you instantiate a module called lambdas for your DSL and your types. You need to give it some more information about how to work with your AST, uh, and then it gives you these auxiliary expressions that you can use. And then, so you take this Scala function and pass it to the library, and it so-called delambdifies it. Now, uh, it's from the library, so you wouldn't need to care about how, but I'm going to give you a, a bit of an idea what it does and also what this expression is. So looking into the library, so the expression, the auxiliary expression is like the expression-centric representation, but very bare bones. It only needs a few primitives. It needs it 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 has variables, but notice I used object here. It would probably you would probably want some information about source position there as well. But the trick is here. Uh, since it's just the temporal, this expression is not used in your AST, just for the translation, you can use globally unique object, and so you avoid any problems with variable, with avoiding variable clashes and such. You need to be able to represent uh, pairs of expressions. You need to be able to access element, first and second element of the pair. And if you have already compiled a function, you need to be able to use that to map an expression. And this is actually all that there is. We don't need any lambda abstraction here because as soon as we encounter a lambda, we recursively delambdify it. Now, what does delambdify do? So what can you do with this Scala function? There's only one thing you can do, apply it to some input. So to get an input of type expression A, create a fresh variable and apply the function to that fresh variable. What you get back is an expression which will look something like this, where the gray boxes are already compiled flows. And now you go eliminate the variable that you introduced. I'll not go into details, but the implementation will traverse this tree and construct the point-free representation, which in this case looks like this. This is the main input. And there could, if this is uh, a lambda inside another lambda, there could be more expressions that were not defined within the scope of this lambda, and those would be returned as well on kind of on the side. This is what this function will be is capturing. All right, so that hopefully gave you some idea what this flow function does. Now we will skip to these extractors. How do we define them and what do they do? So this is our request type definition, and we will need a bit of boilerplate to get those extractors. So for each of the cases, we define them using library. Again, well, you need to, you as the language, this is something the user does. So you will need to define define this function in the partition. We will see how, but just to give you an idea what data the extractor needs to capture. So it needs to know the whole type that that it is a case of. So it represents one case of this ADT, and it needs to know which case it is, but also what are all the cases, like how is the whole type partitioned into cases. That's the kind of data it will hold. And you need to do this for each case, like this one line of boilerplate for each case. Now, as the language author, you need to implement this, but don't worry, there's something, there's an enum module in the library. You need to instantiate it for your types and tell it how to use your types, and then you get this behavior. And now when it is used, so how do we get this syntax? You know, I'm sure you know about the unapply method, which would be an extension method on Extractor. And notice that it always matches, which seems wrong. Because obviously the request, not every request is a for office request, but this for office will always match. That seems strange. But remember, this is only at the Scala level. We will do a bit of translation to avoid this non-totality. And so just to complete how to implement this extractor, we are going to pretend that an extractor is a valid compiled flow, which again sounds like nonsense. And we just map the input to the pattern match by this extractor. Sounds weird, I know. Um, so why do I keep using this superscript? Um, so we will need an AST that has all primitives you wanted, plus ability to represent these non-total extractors as if they were valid functions. And then you need to instantiate lambdas for those. And then this auxiliary expression will be from those enriched lambdas, enriched by extractors. Um, yes, this now means there's a lot of partiality in our AST, but we will get rid of that soon. Okay, so that's how the extractors work. And now finally, uh, how does this switch work? Um, so I was lying to you a little bit about this syntax, but this syntax could be achieved if switch did a little bit of macro rewriting into this form, where the difference is that each case is its separate argument, and don't worry about this extra is function that just used to capture source position for error reporting. Uh, but short of this macro expansion, which I haven't implemented, you will need to write this form, which we will settle for that. Um, um, so given this form, what does switch do? So it uh, um, receives each of the cases as its own function, and now delam delambdifies each of them using a library again. So this is the code you as the language author write, and you use the library to instantiate pattern matching again for your AST, providing some uh, providing operations how to work with your AST. Um, so as I said, it delambdifies each of the cases. And this is now the trickiest part, but also the last part that we need in our puzzle. Um, so by defining each case, you get these subflows, but this non-total, there are these extractors. Um, and they will be at the always at the beginning of these subflows. Um, and now the idea is to break apart these partial flows and recombine them in a way that's total, where there's uh, no non-exhaustivity. To give you an idea what the library does, um, looks at the first extractor in the first subflow. Uh, Remember, the extractor has information about the whole ADT. What are all the cases? All the cases here are for office and work from home. So we group uh, uh, all the patterns based on uh, based uh, based on these extractors for the request type. Uh, Now, okay, we can remove the extractor marking the group from each subflow and apply this recursively within groups. Uh, we get to this picture, and now we are going to form the handlers, the exhaustive by construction handlers. So these two things are actually exhaustive handlers of what? Of this enum. Uh, enum, that's a monitor or chair, in both cases enriched by this desk location. Um, so we this is how we displayed the handlers before. It has a handler of each case, and this desk location is now distributed to each case. We saw a primitive for that before as well. So just to connect it uh, to this rendered representation, because it's slightly different than when I'm drawing it by hand here, we have now constructed this part, this green part of the diagram. Now going up from the recursion, let's go back. So these two pieces are actually exhaustive handling of the request type. So these are again exhaustive handlers of the request type, and again to link it to this rendered representation, we see the correspondence. Um, if there was any non-exhaustivity, we would be uh, somewhere inside the recursion, we would notice there's an empty group. Like if there was no, let's say, work from home or no handling of chair somewhere, that would mean non-exhaustivity, and we would report that as an error. Uh, and final thing is we have eliminated the extractor, and now we can go back to the well-behaved AST that no longer is able to represent partiality. And we are done. I know I glossed over many things, but we went from this Scala-like pattern match to the representation that does not allow non-exhaustivity. So yeah, we have completed this transition, and it's important to remember that this is actually runnable Scala code, and it reports any error before it constructs the representation. So for the case of workflows, what you would persist in your database would be this representation uh, that's already making illegal states unrepresentable. So that concludes this part, translation part, and we don't have time left, but I also said I'm going to say just a few notes about interpretation. Um, so what is now possible thanks to this representation? I didn't talk at all about durable execution of these workflows, but that's very important for that to work properly. So why is this good for durable execution? The reason is simple, because the whole workflow is just pure data, and as such, we can store it in a database. Even when we run the workflow, uh, um, the workflow in progress is also pure data. It has already been applied to some inputs, but the current state is pure data, so we can actually store the current state as we run, and we don't need even sourcing to recover the state. Uh, we have enabled visualization, as I have showed you some rendered pictures, and um, you can make the visualization actually equivalent to code if you want. It's not just like, oh, there's some broad sketch of the program. No, you could go to um, any level of detail, uh, any including when you execute the program, you can visualize it at each step. uh, we haven't talked about concurrency, but that's like left to interpretation. Whenever there's parallel composition, you could uh, evaluate it concurrently. You can do cancellation whenever you ignore something. You can then trace the wire back and cancel anything that's no longer needed. Um, Workflows, so they run, but there's usually in the workflow solutions some ways to uh, query the state of the workflow or issue commands to the workflow, and this is usually done by mutating the state of the workflow somewhere and waiting until the workflow notices. Um, but you could just do it as an additional input of some stream type, like a stream of commands or stream of queries that the workflow, assuming concurrency and some racing, would look at points and handle that without any mutable state. Another thing you could do is workflow templates. By that I mean like parameterized workflows where you would instantiate that template by passing in a value and partially evaluate the workflow on that value. Um, Interactive dry run. Um, so if you wanted to see how the workflow behaves without actually executing the activities, uh, you could execute and pretend you have executed an activity, but then ask the user when the result of activity is needed, like what was it, or uh, or this part of the result, how should I continue, something like that, to give you a better idea of how your workflow will be behaving. And you could go big and decide to, in addition to the Scala embedding, have a specialized graphical designer of workflows. So which will be a lot of work, but you can do that, and then you could load up your existing workflows persisted in database to your new tool without having to rewrite them. Uh, okay, that's all I was going to say about interpretation. Um, and this brings me to conclusion. So the main point, if you're not going to remember anything else, is that if you are going to use Scala functions in your AST, then your embedding is shallow and you're going to hit some limits on what you can do with your DSL programs. So the way out of that is to actually have a deep embedding in which you need to represent functions as actual data. Uh, and then when you go represent functions, there are multiple ways to do that, and some of them give you more uh, more safety by construction, and we saw in this presentation that even non-exhaustivity can be avoided by construction. Uh, so I was only showing you snippets. The code for this lives somewhere in the Libretto repository among examples. I glossed over many details, so I wish this was I could explain this to dummies, but there's you gotta be ready to roll up your sleeves. But uh, I will be happy to answer your questions either now or later on GitHub or wherever. So thank you very much for uh, for attending and yeah, opening to questions.
Right. For now, we don't have any questions.
Okay.
We will wait a couple of minutes because sometimes there are some delays.
Mm-hmm. Well, anyway, so I'll be happy to take any questions also offline via whatever channel you can reach me best, maybe on GitHub in discussions.
Right. I've just shared the link to your GitHub and to your LinkedIn profile. All right. There are no questions, as I can see. So if you will have any later on, as Thomas said, you can just connect with him via GitHub or LinkedIn, so you can ask him. And well, thank you for today, and thank you, Thomas, for being here and for your presentation and sharing your knowledge. And yeah, thank you all for
Yeah,
attending as well.
thank you for organizing, and thank you everyone for joining.
Yeah, and see you in March, because we will have another functional world meetup about Scala. So yeah, thank you all.
Thank you. Cheers.